In part of the lab, you are expected to interact with this simulation. It's easy to interact with it. You just press play first to see how it works. So we have here what's supposed to be a rod and a mass connected to the rod. And this is on a horizontal plane. And then the rod breaks and the mass moves. These look like imprints at the same timed lapses, like every second or every tenth of a second or so. It shows us the position of the object as it was moving, the puck as it was moving. Now we can always restart with this. We can make the circle bigger this way. We can alter where it's going to break in here by acting on this. For example, if I play now, and you can pause it anytime, you can go back, you can go forward step by step. So here we delayed the release time. Okay, so I paused it, and essentially with step by step, you can see how it moved. The question here will be asked you, the questions below will be asked you about the motion of the puck while it was still connected to the rod. Okay, that's when it was still this way. And then its motion after the rod breaks. Now for that, let's talk about this a little bit. Whenever an object goes around in a circle, I have here the Cartesian coordinates x and y, and this is the position of the puck along the circle. Now that puck, if it is speeding up like the puck we had in the simulation, it's going to have a tangential acceleration. And because it's going in a circle, it's going to have a radial acceleration. We also call it centripetal acceleration. The radial acceleration is responsible for changing its direction of motion. That's an acceleration is going to be present for any object that goes around in a circle. And the tangential acceleration is going to be responsible for it speeding up along the circle. And that's not going to be present if the puck is going to be moving at a constant speed on the circle. The puck is going to have a radial acceleration whenever it's on a circle. But in addition to it, if it is speeding up or slowing down along the circle, it's going to have a tangential acceleration. Now, what we have here in pink are other unit vectors. Theta is the unit vector based on the angle theta that the puck is at that instant. And r is the radial unit vector based on the position as well of the puck at that time. So it's pointed outwards, and this is pointed tangential. So a sub t, if it is speeding up, is going to be pointing along theta. If I'm taking a puck here rotating in the counterclockwise direction. So if it's acceleration this way and it's rotating this way, it is speeding up. And a sub t is along theta. The radial acceleration is along minus r. Okay. In terms of mathematically, the acceleration, we write it as a sub t plus a sub r. A sub r, we call it also centripetal acceleration, so most often it is written a sub c. It has a relationship with the velocity at that time. It's v squared over r. This is the speed at that time, r is the radius, and this is the unit vector, minus the unit vector tells us it's pointed in. And I'll talk about this in a second. It is also equal minus r omega squared instead of just v squared over r. Now, omega is what we call the angular velocity. Now, the tangential acceleration that we have due to the change in the velocity along the tangent, it is going to be given by the derivative of the velocity as a function of time. It is related to what we call the angular acceleration, r times alpha. So the overall acceleration is this one here, the derivative of the velocity along theta, plus the centripetal acceleration, this one, times r. Now remember, when we talk about velocity, we talk about the velocity given by, for constant acceleration motion, given by an expression like this. So we have linear motion here along the x-axis, and these are the equations we use for that. Now for rotational motion, we use equivalent expressions. These would be the equivalent expressions for rotational motion. Omega would be the equivalent of v, so it's instead of meters per second, it's going to be radians per second. Alpha is going to be the equivalent of a, so it's going to be the angular acceleration, and it's going to be expressed by radians per second squared. But you notice we have the same expression. The relationship between the tangential quantities and the rotational quantities is this: v sub t is equal to omega r, a sub t is alpha r, and a sub r is omega squared r. The second simulation that you'll be working with is identical to the first one, except you see here the bluish background is to tell us that it is rotating along a vertical plane. It's not sitting on anything, it's just along a vertical plane. But it works the same way. So here, for example, the default setting. And you notice here, we are going to have gravity playing a role. See, this is not a straight line anymore. And if you can get it like to leave from here or here, you are going to see the effect more pronounced. Okay. So that's the second simulation. The third one is a little different. Okay, so we have actually here two crafts. They are supposed to be spacecraft in deep space. No forces acting on them. No gravity, nothing. Now, we can apply forces on them by selecting these. But the forces are going to act on them based on this time. No forces before the first second, but forces after the first second. And we can determine these forces here, and we can change that time here. Okay. Now, I'm not going to act with any force, so I'm going to play. And you see here we have our two aircrafts moving at different speeds, accelerations. They have different motion. We can toggle these to see only one of them. Or the other. Your aim is to change the parameters, and these parameters are going to affect only the red one. The motion of the blue one, the cyan one, are programmed within, are not given. but you are supposed to try to find them by matching the motion. So, for example, if I increase this, the red one is moving faster. So you act on these to match the motion of the cyan one. So for this particular question, the motion is along one direction. So in theory, to be able to compare them, the only things we need to change need to be quantities along that same direction. So we need probably to act on VIX. We can probably act on the time and only these forces, the forward arrow and the backward arrow, if needs be. Okay, notice here the red one is moving at a constant velocity here. Maybe it's worth to see the motion of the cyan one. And we know it's a constant velocity because the markings are the same distance apart. The markings happen at the same time interval, and we see them the same distance apart. So that tells us they are that the cart here is moving at a constant velocity. And you can actually see the values here. Okay, so if I play it again, okay, you see the velocity. Actually, this shows us only the velocity of the red one. Sorry, my apologies about that. Okay, so that's the third simulation. Okay, the fourth simulation, our crafts are going to start here, and we play. Look what happens to the cyan one. And the idea is the same. We are trying to reproduce the motion of the cyan one. So we might need to first alter the initial velocity of the red one so they are matched at the beginning. You see they're not matched. And then decide when to apply the force and for how long. Okay. This is the next one. It's very similar to the one we just looked at, but notice here the motion is different. And again, we need to match it. Probably the first motion at the beginning, affecting the initial velocities, and then the forces. Okay, now this last one is maybe more difficult to see. See, it's very similar to the previous one, but this is not a straight line, it's curved, okay? So like the last one, but it does not keep the same curvature. So there are two motions here. And probably the best way to see it, let's see. Let's give this a force up. And then, yeah, let's keep it like this. Okay. See here, they're essentially similar shapes. I'm keeping the force for this one. And look how this keeps curving while this one does not keep curving. And you'll be able to see that more neatly when you get the same initial velocity at the beginning and match them up properly. That's all.